Okay, I'm Kristen.
I'm Rebecca.
I'm Brooke.
And we chose track and field.
No. No. You don't need to put the space bar in here.
Okay, so you guys might be wondering why we chose track and field, but the correct question is why wouldn't you choose track and field? So me and Brooke are both on the track team, so that's another reason. And when we were debating like what we should do, we talked about track and we kind of took a look at it and we figured out that there's a lot of Calgary track. And there's a lot of different events that you can look at also.
Okay, so track and field is one of the oldest sports, and the first recorded example of track is at sports festivals in the ancient Olympic Games, and the first games were in 776 BC in Olympia, Greece. And these athletic contests were often held in conjunction with religious festivals, as with the Olympic Games of ancient Greece. And for 11 centuries, starting in 776, they were for men only, and they were very popular and prestigious events. The Romans continued this tradition until Emperor Theodosius I banned the games in AD 394. But the true development of modern track started in England during the 19th century, and English public schools and university students gave this sport popularity through their meets, or the British called it meetings. And in 1849, the Royal Military Academy at Sandhurst held the first organized meet of the modern Olympic Games.
Okay, so the first event that we took a look at was the 400-meter dash, and that is one lap around the track. It's about a quarter of a mile, and it was first ran at the modern Olympic Games in 1896. Thomas Burke took first with 54.2 seconds, and his teammate Herbert Jamieson took second with 55.22 seconds.
Okay.
Did you want to follow?
Oh, no, it's fine. It's just, this is Kristen running the Open 400 at Megameet. And you can see she's right here. And we can watch her go around. And so when she was running, I stood in the infield and I timed every one of her 100-meter splits. So I started the clock when she went, and I did a split at right there. I did that was 100, and I did it at 200, 300, 400. And we wanted to find the velocity of her running. So you kind of lose her a little bit right here at the 200 mark, but you'll be able to see her better as she finishes. There you can see her now running again. So there we just made a graph at the top. So at the 100-meter mark, she was at 15.15 seconds. At the 200-meter mark, she was at 31.74 seconds, and etc. And so we wanted to find the velocity of each 100. So since velocity is distance divided by time, we did that for each split. So for example, we did 100 divided by 15.15, and we got 6.601 meters per second, and we did that for each split. And then we wanted to find the average velocity, and average velocity is total distance over total time. So that was 400 meters divided by 64.04 seconds, and we found that her average velocity was 6.246 meters per second. And then now that we know Kristen's velocity, we can prove that she ran 400 meters by graphing the velocity and finding the area under the curve.
So this is just, we graph the velocity. So down here is the time, and on that side is the velocity. So at 15.15 seconds, she was at 6.601. And from then on, we just use that graph to find the area. So finding the area under the curve. The area under the velocity curve is the total distance. So by finding the area under the curve, we can prove Kristen ran the 400 meters. We chose to do the trapezoidal rule because we thought it'd be more accurate than the right or left Raymond sums, because the interval of 0 to 15.5 changes so drastically. And then to find these, we just took the left side of the trapezoid plus the right side divided by 2 times the total bottom distance. And then we found that using the area under the velocity curve, we got 360.951 meters. So it's not completely accurate because the trapezoids aren't always going to be like exactly on the curve. But since our trapezoids were under the curve, it's an underestimate. Then the history of the trapezoidal sum. It's from a group of Newton and Coit's formulas, which is Isaac Newton and Roger Coit's. The trapezoidal method, also known as the trapezoidal rule, is an approximation of the numerical integration. So the idea is to draw a bunch of thin trapezoids, find the area of all those trapezoids, and then add them up.
Okay, so we found out that Kristen's acceleration is positive from the intervals 0 to 15.15 and 31.74 to 47.21 because the velocity is increasing, so that means the tangent lines on those lines are increasing. So that means the velocity is or the acceleration is positive. And we found out that the acceleration is negative on the intervals 15.15 to 31.74 and 47.21 to 64.04 because the velocity is decreasing. So that means the tangent lines are negative and the acceleration is negative.
Okay, so some history of velocity and acceleration. The term velocity is used when one combines the speed of a moving object with the direction in which it is moving. Thus, velocity is a vector quantity and speed may be regarded as the magnitude component of velocity. And Sir Isaac Newton, in his school law of motion, defined acceleration as the ratio of an unbalanced force acting on an object to the mass of the object. And Galileo observed the motions of objects rolling down various inclines and attempted to time these events. He discovered that the distance an object traveled was proportional to the square of the time that it was in motion. From these experiments came the first correct concept of accelerated motion.
Okay, so shot put was first introduced in the modern Olympic Games in 1896 in Rome. And the typical men's high school weight is about 12 pounds and the female weight is 9 pounds. And women finally started competing in 1984 Olympics. And some historians believe that shot put originated from the Celtic tradition of putting the stone, which according to Scottish folklore was used by clan chiefs to help them identify who their strongest men were for battle purposes.
Okay, so this is Brooke doing shot put, and we had to get some measurements, and we were trying to wonder like, how can we measure this, you know? So what we did was to get the first point. We had this really tall measuring stick. So what we did was we had to find where the shot left Brooke's hand. So we had her stand there and act like she's throwing it, and we measured right there. So then it would be, the time would be 0, and then we took that height right there. And then the second point, we took the stick and stood like probably from me to Brooke away, and then she shot it, or she threw it, and we recorded it on Huddle, and then we slow-moed and we watched the shot go across the measuring stick to see how high it was. And then on Huddle, we also got, like, it told us exactly what time it crossed that point. And then the final point we took it was when it hit the ground.
Okay, so this is a graph of Brooke's shot put. And so when the shot put left her hand it was 70 inches, at 70 inches, and that was our time 0. The time that it was at its max was 92 inches, and that was at 0.44 seconds. And then when it hit the ground, it was at 1.1 seconds. And then I found the equation of the graph by plugging the points into our calculator and doing a quadratic regression. So it gave us this equation. And so then the equation is a negative 172.176x squared plus 125.758x plus 70. And then now that we knew the equation, we could take the derivative. And the derivative is negative 344.352x plus 125.758. And now that we knew the derivative, we can find the slopes of the tangent lines at those points and make the equation of the tangent line. So when we plugged in 0, we got the slope was 125.758. So the equation was 125.758 times x plus 70. And then we just did the same thing for each point. And then the instantaneous rate. Using the derivative, we can find the instantaneous rate at any given point. So we just plugged in some points. So at 0.2 seconds, the height was, the slope, the instantaneous rate was 56.887. And then we just plugged random points in there.
And then the history of derivatives, they were also created by Isaac Newton in 1665, and he invented them because the math he was trying to do was too complex for what was already created, so he created derivatives.